This is the screencast for section 4.7, examples 1 and 2. We're studying inverse trig functions. So up until this point, using the unit circle, you've studied trig functions where you plug in an angle and the ratio comes out. So for example, the sine of pi over 6 is 1/2. In this section, we're going to take the inverse trig functions, sine, cosine, and tangent, and we are going to input a ratio and output an angle. So the inverse sine of 1/2 is pi over 6. You remember everything from an inverse from last semester. An inverse, everything associated with x and y exchange places. So domain becomes range, range becomes domain. The x-coordinate becomes the y-coordinate, y-coordinate becomes the x-coordinate. A vertical asymptote becomes a horizontal asymptote, and vice versa. So over here on the right-hand side, I've shown you a basic sine curve. Now what we had to do was cut down the sine curve so it can be 1-to-1. It has to pass the horizontal and vertical line test. The full sine curve from negative infinity to infinity does not. So instead we cut down the domain of a sine curve to be from negative pi over 2 to pi over 2, which, if you remember right, is quadrants 4 and 1 of the unit circle, negative pi over 2 to pi over 2. So basically from a minimum to a maximum. Specifically, the points are negative pi over 2 comma negative 1 and pi over 2 comma 1 at the end points of this reduced sine curve. Now when we take the inverse, the sine curve is going to flip over the line y equals x, this diagonal line here, and now will look somewhat like this. Radians used to be on your x-axis, they are now on your y-axis. Then your output, your ratios, used to be on your y-axis, they are now on your x-axis. So instead of the point pi over 2 comma 1, the point is now 1 comma pi over 2. The domain of inverse sine, or we also call that arc sine, they mean exactly the same thing. The domain will be including negative 1 to 1, and the range will be including negative pi over 2 to pi over 2, the reverse of what the original sine curve is. So now looking at some applications of taking an inverse sine. In example 1, your book asks you to find the exact value of each expression without a calculator. And I have to keep in mind when doing these problems, the only radian values I'm allowed to use are between negative pi over 2 and pi over 2, quadrants 4 and 1 of the unit circle. So part A asks me whose sine, what angle, has the sine 1/2, and that is pi over 6. We just talked about that. The reason why the inverse sine of 1/2 is pi over 6 is because the sine of pi over 6 is 1/2. Now part B is asking what is the inverse sine of negative square root 3 over 2. Keeping in mind that I have to use quadrants 1 or 4, sine is going to have a negative value in quadrant 4. So I have to think about some negative angles. The sine of negative pi over 3 is negative square root 3 over 2. Therefore, the inverse sine of negative square root 3 over 2 is going to be negative pi over 3. Now in C is weird because it looks very similar to what you're used to seeing, the inverse sine of pi over 2. But it's not exactly what you're used to seeing. You're used to seeing the sine of pi over 2, not the inverse sine of pi over 2. This pi is kind of in the wrong spot. It's supposed to say the inverse sine of maybe 0 equals, or 1 equals. So I'm going to take a quicker look at pi over 2. Pi over 2 is exactly approximately 1.57, which isn't in the domain I can use. I can only use negative 1 to 1 for inverse sine. So this does not exist. Now part D is a two-part problem, and I can look at this two different ways. First of all, I do not know what the sine of pi over 9 is, but let's say it's some weird decimal. So the sine of pi over 9 is some funky decimal that I don't know what it is. Well, if then this inverse sine is asking me what angle has the ratio that the sine of pi over 9 has, well, the answer is pi over 9. It's like saying, okay, the sine of pi over 9 is, I don't know, let's say 0.2. So the sine of pi over 9 is 0.2. So what angle has the sine of 0.2? Well, it's pi over 9. Another way to look at this, which we will see later, is a lot of times true, but not always true, is the inverse sine of sine. Sometimes cancel out is the wrong phrase, but they sometimes reduce to just the angle you are taking the sine of. Now in part E, it's asking you to do the same kind of process, and here's why I'm saying sometimes it works and sometimes it doesn't. The sine of 5 pi over 6, let's see, 5 pi over 6 is in quadrant 2. Sine, the y-coordinate in quadrant 2 are positive, so this will be positive 1/2. So this is really asking me for the inverse sine of 1/2. I can't use 5 pi over 6. 5 pi over 6 is not in the range of inverse sine. I can only use negative pi over 2 to pi over 2. So since I'm looking for an angle whose sine is positive 1/2, I need to think of an angle in quadrant 1 on the unit circle whose sine is positive 1/2. And that is going to be regular pi over 6. So this time, it didn't just reduce or simplify to 5 pi over 6, the inside number. We had to have a number that was in the range of inverse sine, or the domain of the adjusted sine curve. Now, exercise 1, the inverse sine of the square root 3 over 2. This is asking whose angle in quadrant 1, because it's positive, of the unit circle, has a ratio square root 3 over 2. Well, that is pi over 3. So the inverse sine of square root 3 over 2 is pi over 3. And then I write over here, this is why, because the sine of pi over 3 is square root 3 over 2. Now there's not much to example 2, and it's now try problem. Just remember to be in radian mode. Also keep in mind, inverse sine is second sine on your calculator. It is not the same as 1 over sine. 1 over sine is cosecant of x. Those are 1 over sine and cosecant are the same, but that is not inverse sine. It is not the same thing, so keep that in mind. I'm actually going to make that red. So then I showed you the rest of the problems. Here, make sure and check your answers.